The heat capacity for any material is referred to as the amount of heat required to change a sample's temperature. And so right here we can see a few different variables that are going to be at play here. So we have the amount of heat, so that's going to be our energy amount. Then we have a sample, and any sample has mass, it has volume. We're specifically going to focus on its mass, and it will have temperature. So we're going to have heat, mass, and temperature all working together when we work with heat capacity or specific heat capacity for a given material. So every substance has its own, and it's measured in joules per gram degree Celsius. And there again, we see all three of these variables. We've got that energy is joules, we have the sample grams, and we have the temperature in degrees Celsius. And then we have a couple more terms listed here, an insulator and a conductor. An insulator is a material in which lots of heat is required to change the temperature. So that means we're going to have a lot of joules of energy needed. Therefore, our heat capacity will be a larger number for an insulator. For a conductor, however, the heat changes the temperature very easily, so we won't need as much energy, and then you might have a really small amount of joules per gram degree Celsius. Therefore, our specific heats for conductors are going to be much smaller. So let's look at these examples here, and I'm going to hop through some of these because once we start doing a couple of the same problems, you'll see the train of thought is the same throughout this whole worksheet, and then we'll look at the math on the last few problems. So there are 2 spoons in a pot of water on the stove. If the specific heats of the spoons are 0.189 and 1.76 joules per gram degree Celsius, which is the specific heat of the wooden spoon and which is the specific heat of the metal spoon? Keep in mind that wood is an insulator and metal is a conductor. Okay, so based on what we have in our box at the top, we know that wood is an insulator, so it's going to require lots of heat to change the temperature. That means it needs to have a higher specific heat, meaning it is going to be able to hold heat much better and require more to raise its temperature. And that's why it's easier to kind of hold wood that's been heated. It still can get pretty hot if you leave it in there too long, but it can kind of, it won't burn you as quickly as if you were to grab a metal spoon if you'd put them both in to your boiling water at the same time. So our wood is going to have the higher heat capacity here, or our higher specific heat, 1.76 joule per gram degree Celsius. And that leaves metal to have the 0.189 joules per gram degree Celsius for metal. And we know that because the metal is a conductor, so its temperature changes very easily. It does not have as high of a capacity to hold heat before it is influenced in its temperature. So the same thought process is used for numbers 2, 3, and 4 on our page here. 2 is kind of an extension of number 1. Would you want the handle of your cookware to have a high specific heat or a low specific heat? We just had kind of discussed that with wood metal, so I'm going to leave that for you to do on your own. Number 3 says, consider the following specific heats of metals. If the same amount of heat is added to the same mass, 100 grams, at the same starting temperature, which metal will reach the highest temperature? So we've got same joules being added, same mass, and the same kind of temperature change that's going to happen because they start at room temperature. Well, I guess the temperature change is going to have to be different because all of the rest are the same. And so we want to know which one is going to end up being the highest temperature, which one is the most easily influenced or can hold kind of the least amount of heat before its temperature starts to increase. So we're going to actually be looking for the smallest specific heat value in our table because those are going to be the ones that are easily influenced and reach a higher temperature. So that means our answer here looks like is going to be gold. That will reach the highest temperature. If it asks us for the lowest temperature, now we're going to want to find the material with the highest specific heat, which would be chromium. It still isn't going to be that insulated because all of these are metals. They're all going to be pretty easily influenced. As you can see, they're all less than 1, but gold is going to be the highest temperature after being heated for the same amount of time. I'm going to let you do number 4, same kind of idea, 2 objects sitting in the sun. Object A heats up quicker than object B. Does it have a higher or lower specific heat than object B? 5, 6, and 7, and 8 actually all go together. This is where we're going to actually start doing math problems about specific heat. And we have not actually done this before in terms of figuring out an equation from its units, but you can do this process for any calculation or any measurement that you know its units. So we have the units, joules per grams degrees Celsius, and the question asks what variables could be used to calculate it. Well, let's just pull apart all of the units that we have in this, or the variables that we have in this unit. So joules is energy, and it's got a slash, which is just division. Then we have grams, that's mass, and we have degrees Celsius, that's temperature. And since they're right next to each other, that is showing us they're being multiplied together. So our variables have energy, mass, and temperature, and so we can actually put together this equation here to find the specific heat of anything that we have the energy, mass, and temperature of. And like I said before, you can do this for anything that you have the units for. If you know the variables, then you can find out an equation because that is how they're related to one another. So if we have an energy, mass, and temperature, we can find the specific heat. That's what we're going to do in number 6 and number 7. 6 says, if a beaker of water absorbs 83.68 joules of energy, raising the temperature 2 degrees Celsius, what is its specific heat? We have an energy value, 83.68, so I'm going to put that in for energy. We have a mass, it's 10, and we have a temperature change. I didn't write that here, but this is a temperature change. We are going to either have an increase or a decrease since we're talking about transfer of temperature. So this one just tells us it raises 2 degrees Celsius. So we are ready to do our math. We're going to do, 10 times 2 is 20. I'm going to go ahead and simplify that there. And now we're ready to find the specific heat of this water, which ends up being 4.184 joules per gram degrees Celsius. Ta-da! So there's our specific heat based on the units. We were able to figure out this little equation here. I want you to do number 7. It's the same process, just a different amount of energy, different, actually it has the same mass and the same temperature change. But this will result in a different specific heat for the ice cube. Then number 8 wants you to review your answers and tell us if ice or liquid water requires more energy to raise its temperature. And you'll answer that based on the specific heats that you have in number 6 and 7. If something requires more energy to raise its temperature, that means it's going to have a higher specific heat. It's going to be more stubborn. Needs to be more joules per gram degree Celsius, more energy in order to raise its temperature. So you're looking for the larger specific heat for number 8 to tell us if ice or if liquid water is going to be the one requiring more energy to raise its temperature.